Alright, so for part two, we will talk about elastic collisions. And again, the idea here is that kinetic energy before and after the collision is conserved because the bodies are only temporarily deformed. They unspring after the collision, and all of the elastic energy stored is then transferred back into kinetic energy. So what you can do in that case is you can write down an equation for conservation of momentum, and as Knight does, we're going to consider mass 2 to be at rest during the collision, and mass 1 having some velocity Vix 1. The first equation represents conservation of momentum. So just in words, the final momentum of particle 1 of mass 1 plus the final momentum of mass 2 was equal to the initial momentum of mass 1 because mass 2 was at rest. And then that's conservation of momentum, and then conservation of kinetic energy would be the final kinetic energy of mass 1 plus the final kinetic energy of mass 2 is equal to the initial kinetic energy of mass 1. Again, remember that mass 2 is initially at rest. And so what we have here is we have two equations and two unknowns. If you know what Vix is, and if you know what M1 and M2 are, one can then solve for Vfx1 and Vfx2. And the result is Vfx1, that would be the final velocity of mass 1, is m1 minus m2 over m1 plus m2 times the initial velocity of mass 1, Vix1. And the final velocity of mass 2, Vfx2, is 2m1 over m1 plus m2 Vix of Vx1, which is the velocity of mass 1, initial velocity of mass 1. So if you'd like an exercise in algebra, you can derive these equations on your own. Otherwise, you can just take them as given. So what we're going to do here is talk about three different cases for this equation. And so what I will consider is I will consider first of all the scenario where you have a pool ball moving and hitting a stationary pool ball head on, and not a glancing collision but a head-on collision. So in other words, their centers would be aligned with the velocity of the first ball. And in that case, the two masses, m1 and m2, are both equal to little m. And so if we put that into these equations that we just wrote down, that would mean the final velocity of the first ball, which is moving, is little m minus little m over little m plus big M times its initial velocity, which is 0. And then the final velocity of the initially stationary pool ball would be 2 times little m over little m plus little m times the initial velocity of mass 1. And so you can see that the multiplier here for the velocity is 1, and therefore the overall effect is, if you have a head-on collision between a pool ball and a stationary pool ball, that what happens is the pool ball that was initially moving is at rest, and the velocity of the initially stationary pool ball is now the same as the velocity of the initial pool ball. That's predicted from our elastic collision equations. That's one case. We want to consider three cases. Second case is, let's say we had a solid steel ball hitting an equal size ping pong ball. Well, clearly in that case, little m1 would be the steel ball, little m2 would be the ping pong ball, and m1 would be much, much bigger than m2. And so just to kind of emphasize that, I'm going to take little m1 to be big M and little m2 be little m. And if we put those numbers, those symbols into the equations above, we get the final velocity of the solid steel ball is big M minus little m over big M plus little m times its initial velocity. But that's roughly equal to its initial velocity. So in other words, the velocity of the pool of the steel ball before and after the collision is about the same. On the other hand, the velocity for the ping pong ball is 2 times big M over big M plus little m times the initial velocity of the steel ball, and the multiplying factor here is roughly 2, and so the velocity of the ping pong ball after the collision is twice the initial velocity of the steel ball. Maybe we can do these experiments in class here. Okay, so the last case is where we have a ping pong ball hitting an equal sized solid steel ball. And in that case, you'd have little m1, that would represent the ping pong ball, much less than little m2, which would represent the solid steel ball. So we'll turn things around here, and we'll take little m1 equal to little m, and little m2 equal to big M. And again, putting those symbols into the equations we have, the velocity of the ping pong ball after the collision would be a little m minus big M over little m plus big M times the initial velocity of the ping pong ball. And the multiplying factor here is roughly -1, and so that means that the ping pong ball is going to recoil with a speed roughly equal to its initial speed, but in the opposite direction. And the other equation, this would be the final velocity for the solid steel ball, would be 2 times little m over big M plus little m times Vix1, and that's going to be roughly 0. And so the result is that the ping pong ball is going to recoil with an equal and opposite speed relative to its initial speed, and equal and opposite velocity. And the solid steel ball will, to good approximation, remain stationary.